All right, we're going to continue our look at exponential and logarithmic functions. Today we're going to do it in the context of financial models. So everything we talk about today is going to deal with money. Okay? Our first objective today is that we can determine the future value of a lump sum of money. As we do this, I'm sorry that I don't have time to go into a real detailed description of how things work when money is borrowed or lended. But basically what we need to know is that an amount of money borrowed or lended is called principal. And it costs money to borrow money from someone. You pay money when you take out a loan for college or for a car or a house. You pay money when you take out a loan in the form of a credit card. This is known as paying interest. You may not know that banks also borrow money from you when you make a deposit in a savings account. Or when you buy a certificate of deposit, you are loaning money to the bank so that they can further use that money to profit. And the bank pays you interest for that. You can also loan money to businesses and to governments in the form of a bond. You've heard of buying bonds in the financial market, perhaps. A bond is just a loan. And when you loan money to someone, again, that money is called the principal. The person who borrows the money needs to pay interest on that. So I'm sorry that we can't get more in depth with that, but I hope at least you have a basic idea of the idea of principal and the idea of interest. The first type of interest we study is known as simple interest. And simple interest is just calculated by multiplying the principal by the interest rate paid by the time of the loan. So it's just a product. If you look at these definitions for our variables, you can see I is the interest that is charged or earned, depending on if you are the lender or the borrower. P is the principal that we discussed earlier. R is the interest rate per year. Now that's going to be expressed as a percentage, and when we use it mathematically, we'll want to use a decimal for that percentage. And T is the time in years. It's important that these two units of time match, because as we do our unit analysis and multiply, this is going to be years in the denominator. Notice it's per year. And this is years in the numerator. And we want that common unit to divide out. So that's why we need to make sure these agree. The most common unit of time to use is years, or as they say, annually, or per annum. So the first example I'm going to give you today is not out of the textbook. This is one that I've created to give us a look at simple interest. It says a savings account pays an interest of 2% per annum, compounded quarterly. If $1,000 is deposited, how much is in the account after 1 quarter? So since only 1 quarter is passing, we do not yet need to worry about this idea of compounding. I haven't even discussed that yet. Instead, we have a simple interest situation where the interest paid equals principal times rate times time. And now I'm just going to evaluate this by substituting and simplifying. So you can see I've substituted in the principal of $1,000. I've included my unit of currency there. The interest rate was 2%, which is 2/100ths. And the time was 1 quarter of a year. Remember, that's 1/4. Multiplying those gives me an interest of $5. Now the question asked didn't say how much interest is earned. It asked how much is in the account after 1 quarter. So the account still contains the principal of $1,000 plus the interest of $5. So the account contains a total of $1,005. I'm going to set this on the screen so that you can see everything we've talked about with simple interest. Go ahead and pause the video and record this information about simple interest. All right. The next thing we need to talk about is the idea of compound interest. So in that above example, after 1 quarter of a year has passed, the account no longer has $1,000 in it. It now has $1,005. So if you're going to continue to earn interest in that account, you're going to earn what's known as compound interest. Compound interest is interest that is paid on the principal and on previously earned interest. because now that money is in the account. If you are a borrower, compound interest can be very dangerous for you. Credit cards are a great example of this. If you are a lender or an investor, compound interest is your friend, and it's what's going to allow each of us to invest wisely and retire comfortably. So, we're going to look at the previous example that I had. This is now in the book, and what's going to happen is they're going to take this, and instead of using 1 quarter for our time, they're going to use 1 year. So, the first quarter we already discussed. The first quarter gave us an account balance of $1,005. If I want to look at the second quarter, now the money in the account, the principal is $1,005 times 2% times a quarter of the year. The interest paid for this second quarter would be $5.03. Basically, the extra 3 cents of interest is the interest paid on the previous interest. So now, third quarter of the year, my account balance has $1,010.03. That's taking the previous balance and adding this interest, times the interest rate, times the time. And in that quarter, I'm going to be paid $5.05 of interest. For the fourth quarter, I've now got a principal that contains all of the previously earned interest, times my interest rate, times my time, earning me $5.08 in interest. That means that after 1 year, the account balance is going to be $1,020.16. Notice that in each quarter, the interest paid was higher than the previous quarter because it was being paid not only on the principal, $1,000, but on all of the previously earned interest. And that's why it increases each quarter. And that's the power of compound interest. Go ahead and pause the video. Okay. This next little bit of notes might be a little challenging to follow without the textbook. This is going to be the basis for taking what we just did for a year and generalizing it in a way that doesn't make us calculate our interest step by step by step. Imagine if we had done the previous example and wanted to do it for a time period of 5 years compounded quarterly. That would have taken us 20 iterations of that algorithm. We don't want to do that. So, a challenge to follow this perhaps without the book. Do your best to use this video with the book to understand. Alright, so we're going to look at in compounding periods per year. So if we tell you we're compounding quarterly, in is 4. If we tell you we're compounding monthly, in is 12. If we tell you we're compounding daily, in is 365. So for in compounding periods per year, all right, one compounding period is simple interest. Principal times rate times time. Notice for the time, I'm using the fraction of a year divided into the number of compounding periods. In the previous example, that was 1/4. Okay? Multiplying these two, I can multiply fractions here, simplifies this to P times the fraction rate over number of compounding periods in a year. P times R over N. So that's the interest for one compounding period. The principal then, added to the interest paid, gives me the account balance. So my new balance equals my original principal plus the interest that I just earned above. Notice how this comes there. Using the distributive property, I can factor a P out of both of these two terms and rewrite that as P times the quantity 1 plus R over N. So that's my account balance after one compounding period. If I have a second compounding period, this is where things can get a little bit trickier to follow. This amount of money in the account comes from here. Then I need to take that same amount and multiply it by my interest rate over the number of compounding periods in a year. That's repeating this process again. When you look at this in your textbook, They're going to describe this to you as the new principal here and the interest on the new principal there. Now, the common factor of these two terms is a little more complicated. It's both P and the binomial 1 plus r over n. So if I factor out both the P and the 1 plus the r over n, I end up with P times 1 plus r over n multiplied by 1 plus r over n. And then those two factors can be written as 1 plus r over n squared. This is the formula for two compounding periods. Repeating that process for a third time, without detailing the steps again because they are the same, I end up with this P times 1 plus r over n to the third power. And we can start to generalize that each compounding period is going to multiply an additional factor of 1 plus r over n. Notice how we have progressed through here. And so if there are n compounding periods, then the amount in the account is equal to the principal times the factor of 1 plus r over n raised to the power of n. That tells us the amount in the account for n compounding periods in 1 year. If we take that even further to t years, the number of compounding periods will be n, which is the number per year, times t, the number of years, and that gives us our exponent nt. So in your textbook, you can see this highlighted formula listed as the compound interest formula. And I will not ask you to derive it like I've done above. That's pretty good mathematics if you can understand that derivation. But I will ask you to use this formula correctly. Let's go ahead and put that formula to work. So, example problem number 2. Example 2 says, investing $1,000 at an annual interest rate of 10% compounded annually, semi-annually, quarterly, monthly, and daily will yield the following amounts after 1 year. So I'm going to begin by investing this and compounding annually. That means my principal is $1,000, my interest rate is 10%, the period of time is 1 year, and compounding annually means n is equal to 1. I'm compounding 1 time per year. My compound interest formula, substitute my values from above, and simplify. I can enter this entire formula into my graphing calculator in order to simplify this. I hope that this makes sense, that there's $1,100 in the account, because if the interest is 10%, 10% of 1,000 is 100, and compounding once per year means that I won't get to experience any compound interest in only 1 year's time. In part B, I'm asked to compound semi-annually. That means I'm compounding 2 times per year. So the only thing that's going to change is n is equal to 2. So I'm going to substitute the values into the same compound interest formula. Notice that I've used 2 times per year as my n value, and simplifying gives me an account balance of $1,102.50. The additional $2.50 is because I have compounded 1 time, whereas up here I did not get to experience compound interest. All right. I'm sorry, I've compounded twice. My apologies. Okay. Pause the video here, record portions A and B in your notes, and then on your own, please finish this example for quarterly, monthly, and daily compound interest. All right. Here's my work for quarterly, monthly, and daily compound interest. Compare my work to your work. Make sure you've accurately rounded to the nearest penny since we're dealing with money. What do we notice about each answer as the number of compounding periods in a year increases? I hope you noticed that the amount in the account goes up as I compound more frequently. And as we look at compound interest, the more often our interest can be compounded, then the more interest is going to be due from the borrower to the lender. So our last part here used 365 times, all right, compounding once a year. Well, what if I could compound hourly, or by the minute, or by the second? That leads us to our next question. What happens as the number of compounding periods in a year approaches infinity? What if I try and compound as often as possible? This is the second derivation that I'm going to show you. And again, this may be a little easier to follow if you use the textbook as well. This is the bottom half of page 327. So in 1 year's time, the amount in our account is equal to our compound interest formula, with t being 1. I know it looks a little bit strange, and you may not be sure why I've done this, but I'm going to rewrite r over n as the reciprocal of n over r. So all I've done is rewrite this fraction, r over n, as the reciprocal of n over r, 1 over n over r. The reason I'm going to do that is because I have this exponent of n here, I am going to take the rth root of this factor and then raise this factor to the r power. Notice how I have done that. These two steps are equivalent to one another. Now, I'm going to define a variable. You can arbitrarily choose any letter you want. You can choose x if you wanted. I've chosen h to match the book. And I'm going to let h be this fraction n over r that we've used twice. So substituting h into our formula gives us this. The reason we have done this is we're discussing what happens as n approaches infinity. I hope that as you guys look at this, this is getting familiar to you. 1 plus 1 over h to the h power, we know that as h gets closer and closer and closer to infinity, the value of that expression gets closer and closer and closer to the natural base e. When we introduced the natural base to you, we said that it had a lot of applications in financial models. This application in compound interest is one of them. So this entire expression, 1 plus 1 over h to the h power, gets closer and closer to the natural base. So I can rewrite that formula as a equals p times e to the r power. A equals p times e to the r power. If we want to allow this to happen over t number of years, then we have a number of compounding periods. We need to multiply that exponent by t. And that gives us the formula for continuously compounded interest. This is on the top of page 328 in your book. The amount in the account equals the principal times the natural base e raised to the power r times t. I can't get this all on the screen at once for you here. So let me slide this up really quick. You can record that derivation. And now I'll slide it down just so you can catch that continuously compounded interest formula. All right, let's put that formula to work. Example 3 in your textbook. Oh, that sounded magic. Example 3 in your book says the amount A that results from investing a principal of $1,000 at an annual interest rate of 10% compounded continuously for a time of 1 year. So now I've used the same values from our previous example, but I'm continuously compounding, so I'm going to use the formula with the natural base e. That means that as I substitute and simplify, the amount in the account will be $1,105.17. If you remember, daily compounding gave me an account balance that was 1 penny less than this. So even though the difference isn't large, we can see that continuously compound interest is going to pay more interest for us. Please pause the video and record this example. All right. Second objective is to calculate effective rates of return. The reason we calculate effective rates of return is it can be hard to compare different different accounts when we look at interest rates and number of compounding periods both varying. So what we do in order to make the comparison easier is we convert each one of these rates to a simple interest rate. In order to do that, all you need to do is calculate the compound interest and then put that into the I in the simple interest formula and solve for the interest rate in the simple formula. All right? The simple way, or the formula that describes what I just said, is right here for each of these. R sub E is the effective interest rate in an account, and you can see that the information for each of those interest rates comes from our compound interest formula, and then we need to subtract 1 to take into account our principal. In example 4, we are asked to compare 3 different bank accounts. We are asked to compare a 5-year certificate of deposit from American Express offering 2.15 interest compounded monthly, First Interstate Bank offering 2.20 but compounded quarterly, or Discover, which offers 2.12 compounded daily. It's tough to compare these 3 accounts because each pays a different interest rate and has a different compounding period. In order to find the effective rate of return, for example, in the American Express account, I'm going to use my equation, substituting in the interest rate paid and the compounding periods, 12 per year, and I get an effective interest rate of 0.02171. Obviously, we can convert that decimal to a percentage. Will you please pause the video here, make sure you've recorded the effective rate of interest formula and the beginning of example 4, and then on your own finish example 4 for the effective interest rate for First Internet Bank and for Discover. Okay, here's my work for First Internet Bank. We can see that the effective interest rate is slightly higher than American Express. So First Internet Bank is going to pay more interest on the certificate of deposit than American Express is. Continuing our work with Discover, we can see that Discover pays a lower interest rate than either one of American Express or First Internet Bank. So the question asked us which of the 3 banks is going to pay the highest effective interest rate, and we can see that First Internet Bank offers the highest effective rate. Converting the decimal to a percentage, it's approximately, I wrote the wrong one, 2.218%. Sorry about that. Glad we caught that. All right. Third objective. Determine the present value of a lump sum of money. Because borrowing money costs interest, that means that money needed now is worth less than money in the future. I think I just said that backwards. Money now is worth more than money in the future. Sorry about that. To find the present value of a future lump sum of money, all we need to do is take our compound interest formulas and isolate the variable P. Looking at the compound interest formulas, to isolate P, all we have to do is divide. We divide by our interest, 1 plus r over n to the nt power. When you look at my notes on the screen, you may say, but Briebach, you didn't divide. Well, what you see here is I have raised this to the negative nt power. So I am multiplying the account balance by the reciprocal of that factor. Remember, dividing is the same as multiplying by a reciprocal. You could write each of these two formulas as division if you preferred. All right, now that you've got those two present value formulas, let's put them to work and show you what I mean. Example 5 says a zero coupon, which is a non-interest bearing bond, can be redeemed in 10 years for $1,000. How much should you be willing to pay for it now? Okay? So what happens is, if the bond is worth $1,000 in 10 years, we would not pay $1,000 for it now, or we're loaning our money for 10 years for free. So instead, we're going to pay less now than we would, we're going to pay less now than $1,000 so that when they pay us back in 10 years, they have paid us interest on our loan. The first thing we're asked to do is compound this monthly. So when I look at compounding monthly, I'm going to use n equals 12, substitute all my values into this formula from above. So if this final value is going to be $1,000, then compounded monthly, in order to earn 8%, I would only pay $450.52 for the bond now. That might surprise some of you, that in 10 years, I'm expecting to receive back more than double what I loaned here. But that's the interest I would earn at 8% compounded monthly for 10 years. Please pause the video, record example A, and then do example 5B on your own from the book. All right, here's example 5B. Please compare my work to your work. Make sure that you're comfortable using the present value when we are compounding continuously. Notice that we're earning 7% interest here, and we would pay just under $500 today if we were going to receive $1,000 in 10 years if our rate of return was to be 7% compounded continuously. Last objective. The objective says we're going to determine the rate of interest or the time required to double a lump sum of money. Now the truth is, we don't need to just use multiplying by 2 here. We can double our money, we can triple our money, we can find out how much to have 1.5 times our money. It doesn't matter as long as we understand that we're going to have some factor of our current principal. Example 6 says what annual rate of interest compounded annually is needed in order to double an investment in 5 years. So we're asking, what rate of return would you need on your investment to double it in 5 years? Well, if I'm doubling my investment, that means my account balance needs to be 2 times the principal. So I've substituted 2 times P in place of A. This was compounded annually, so n equals 1, and the time period was 5 years. Simplifying this, I can divide both, I can simplify r divided by 1 and 1 times 5. And then I can begin to solve for r by dividing both sides of my equation by p. That gives me 2 equals the quantity 1 plus r to the 5th power. This is a polynomial equation. I can solve it by taking the 5th root of both sides. That'll get me my real answer. Excuse me. So the 5th root of 2 is equal to 1 plus r. Subtracting 1 from both sides of the equation tells me that the 5th root of 2 minus 1 is equal to r. And simplifying that, or approximating that on my calculator, tells me my interest rate needs to be about 0.149. I'll convert that to a percentage when I write my answer and see that an annual interest rate of 14.9% is needed to double the principal in 5 years. That would be an incredible return on your investment for most years. You would be very happy to earn 14.9% on your investments. Go ahead and pause the video there. Make sure you have example 6 in your notes. All right, last example, example 7. Similar situations. Example 7 asks, how long will it take for an investment to double in value if it earns 5% compounded continuously? So the contrast between example 6 and example 7 is in example 6 I was compounding annually. Here I'm compounding continuously. So that means my base is going to be the natural base E. I want to double my investment, so I need the account balance to be 2 times the principal. The principal is multiplied by E to the exponent 0.05t because my interest rate was 5%. I'll divide both sides of the equation by P. Now I need to solve for t, and t is in the exponent. This is an exponential equation. We've been working this chapter to solve these. I'm going to use the definition of logarithms to rewrite this. 0.05t was my exponent. That's equal to a logarithm base e of 2, or the natural log of 2. The last step to solve for t is to divide by 5%. T equals the natural log of 2 divided by 5%, which is approximately 13.86. That means it'll take about 13.86 years to double the investment. Please pause the video and record part A of example 7, and then do example 7b on your own. It's the same information. We're asking how long it will take to triple the investment. All right, here's my work for part B. As we triple our investment, please compare that to yours. Make sure that you're comfortable with this information. Thanks for listening today and learning a little bit about how we can use financial models with exponential and logarithmic equations. Hopefully we have learned a little bit about interest and will be able to profit in the future from that knowledge. Have a great day and stay healthy.